I'm Soumith Chintala. I'm here at the PyTorch Dev Day with a very special guest. I've been working in the PyTorch community for the last 5 years, helped start and fund the project. And today with us, there's a very special guest who is no other than Yann LeCun. Yann, I've known him for over a decade. He has been my mentor. Yann LeCun has been one of the pioneers of deep learning who has started this whole new cycle of AI, and he has won a Turing Award for it, the highest award given in computer science. And on top of that, Yann LeCun is the chief scientist of Facebook and a professor at NYU. Just to step back a little bit, that's not what I'm really excited about to introduce Yann here today. Yann built a bunch of frameworks in the 80s and in the 90s that actually are the foundations for a lot of ideas in PyTorch. So the frameworks he built, Lush and SN, that I know of, and I'm sure he'll talk about more of that stuff, that they have been like fundamental in shaping our ideas. And like if you're using PyTorch today, you're sitting on, you're using on some of the ideas that Yann has come up with. So with that, I want to just quickly check, Yann, do you have anything else you want to add on a personal note?
It's a wonderful introduction. You know, I don't have anything to add, other than the fact that some functions in PyTorch have the same name as the stuff that I wrote back in 1991.
Nice, very cool.
Yeah, my interest in writing deep learning frameworks, as we call them today, goes back to 1983. Wow. Which is when I wrote the first one. It was called HLM, actually, and it could do backprop and various other things. But then I realized that I could not really control it very well. It had a very simple command language. It was written in Pascal. And it had a simple command language. And I realized, like, I need to have loops, and I need to have functions, and I need to basically have a programming language. So I started, studying what front-end programming language could I use for my next generation neural net simulator. And I almost settled on Forth, okay, but eventually settled on Lisp.
Nice.
Because it's easy to write your own Lisp interpreter. We're talking about 1987, and there was no Python, there was no MATLAB, there was no language you can just download off the internet. There was no internet. And use as a front-end language, you basically had to write your own. So I got together with Léon Bottou, who is at Facebook, and we wrote a Lisp interpreter and then hooked up a sort of numerical library for kind of neural nets, very specialized for neural nets in the back. Then I moved to Toronto, and I kind of finished it, and Léon, on his side, kind of kept working on it. So that was called SN, for simulateur neuronal. This was kind of the French word, the French name. And then Léon had this idea in 1991, roughly, that the right way to build a neural net or a deep learning system, it wasn't called deep learning then, was to basically have functional modules that you assemble in graphs, and then you get this kind of automatic differentiation. They don't have to be neurons and weights and stuff like that, right? And I started implementing that, and he implemented the back end. So this was in the early 90s. And that kind of ended up with help from Patrice Simard and various other people in a system called SN2, which eventually we open sourced in the early 2000s under the name Lush.
Nice.
And a lot of people kind of, that was sort of the inspiration behind Torch.
Yeah.
The first Torch, which had a Lua language as the front end. For Café 2, or for Café 1, actually, and Café 2 within Facebook, and then later TensorFlow and PyTorch. So, they all use this model of you assemble blocks and you kind of differentiate automatically. Somehow.
Nice. So a couple of nerdy questions before we move on. So HLN and SN, at least HLN, I presume, was not floating point, or was it?
It was floating point, but very slow, because at the time the machines couldn't do that very much. So it had a mode where you could turn on fixed point, because that was much faster.
And did you guys usually train in fixed point or floating point?
We were, whenever we were experimenting, it was floating point. Like even the first version of SN had you could switch the mode from floating point to fixed point. And because you have to realize, Leo and I developed the first version of SN on a Commodore Amiga. Okay, we both have Amigas, and those things had a 68,000 processor, but no floating point accelerator. So floating point was really slow. So we had a fixed point mode. And then, we ended up having Sun workstations and stuff like that were floating points. So it was.
And did you guys have any accelerators you use, like DSPs or any other accelerators?
So that came a little later. So I joined Bell Labs in 1988, and started experimenting with convolutional nets and things like that. And then we wanted to build. After the first results of convolutional nets to do character recognition, we wanted to build a demo so we could show to the engineering groups and the product groups and stuff like that at AT&T. And so with a few engineers in the group, I wrote basically what amounts to a compiler that would take the convnet, prune it, suppress the small weights, and then basically generate a self-contained piece of C code that we could compile on a DSP board.
Nice.
Because at the time, the PCs were incredibly non-powerful. We're talking 1991, roughly.
Not even mainstream GPUs.
No GPUs, and even the GPUs were slow. So it turns out AT&T was building a DSP chip, and I was selling a board with a C compiler, and that DSP was capable of 20 megaflops, which was completely amazing at the time.
That is.
You couldn't even get that in a workstation.
Yeah.
You were getting maybe 2 or 3 megaflops in a workstation, but certainly not 20. So we would put this in a PC, and then we had this demo. There's a video on YouTube where you see me put my list of numbers under a camera and hitting a key, and that's running on the DSP, and it had a compiler and something that kind of makes the computation cheap enough.
Very cool. So we've gone through a ton of breakthroughs and research in the last 2-3 decades, mostly in the last decade. So I'm sure you've seen it all. You've seen a lot of things go on. What's top of your mind right now?
Well, so it's no secret that I'm sort of a big supporter of this whole idea of self-supervised learning. And I see this as one of the 2 or 3 main problems that are kind of, that we need to go beyond if we want to make true progress towards kind of more intelligent systems, right? So one is allowing machines to learn like humans and animals. Currently, the type of learning paradigms that we use are really not nearly as efficient as what we can observe in humans and animals. So that's one problem that we need to solve. Second problem we need to solve is allowing machines to reason in ways that are compatible with deep learning and gradient-based learning more generally. And so, for tasks that they're not like perception where, you show an image, you get an answer. But tasks where you need to plan, you need to reason.
Yeah. And
it's not entirely clear how to do that. And there is big conceptual battles about what the best approaches are for that. Yoshua Bengio is interested in that as well. And there's a lot of work at Facebook and various other places on how you do this. And then there is a third problem, which I think is not being really addressed at all, which is that with the type of deep learning that we have today, we can train machines to represent the perceptual world, but we don't have any ways to train them to represent the world of actions, or the world of action plans, I should say, right? So, you want to get from here to San Francisco, you know that you have to go to the airport, blah, blah, blah.
Right.
You're going to decompose this task into subtasks, right? And all the type of tokens that you use for those subtasks are things that you learned. They're not things that you were born with, right?
Yeah.
How do we get machines to learn those representations for action plans?
Right.
So that's the third problem, I think. But this one is kind of some way down the road.
Yeah.
The first one really we have to solve is how do we get machines to learn how the world works? How do we get them to learn, accumulate a lot of background knowledge about how the world works through observation, training them to represent the world, so that whenever a particular task shows up, we don't need to train them with millions of examples. We can, like a small child, you show the small child a couple photos or drawings of an elephant. Yeah,
that makes sense. So a couple of clarifying questions here. So for the second and third task, like I think they're somewhat related to each other. Like, are you? So there's a general. This area obviously has gotten a lot of interest. So people are talking about, should we use deep learning for the first part, like the perceptual stuff, and then use symbolic AI, like classical, like the COQ, or like various languages and projects from back then. I think like AI has seen a phase of symbolic AI being at its peak with fuzzy language and stuff like that, right?
Right.
So do you think, are you saying there would be a hybrid, or are you saying there would be just learning methods with the right representations that would just do all of the like discrete planning and stuff like that?
So I think it's entirely possible that there will be systems, perhaps in the short to medium term, that will combine deep learning, sort of pure deep learning things with kind of more classical, good old-fashioned AI, if you want, or symbol manipulation. But there is a lot of evidence that even deep learning systems can do symbol manipulation to some way, in some way, without necessarily being explicitly driven to do so, in a sense that we don't have to hardwire the symbols into the system. So there's this experiments that were done by our colleagues on, can I do symbolic integration of a differential equation using a transformer, train a transformer to do this, and you can, and it works, which is pretty incredible. So I think ultimately the solution I would prefer is one in which the reasoning part is done with not with symbols, but with vectors, essentially, right? Patterns of activities and whatever. And this is not, my idea or anything. Jeff Hinton has been advocating for things like this for 40 years. So not a new concept. The question is, how really do you do it? How do you make reasoning compatible with deep learning, essentially, with gradient-based learning, whether it's deep or not?
That gives a lot of interesting perspective into how you're thinking about, I think, your priorities on like what we need to make progress in AI. Did you have any thoughts on all the fundamental stuff that's already been broken through within the context of machine learning and AI, and the applications of it? Like, not just the like more fundamental, how do we get to superhuman intelligence, but how do we exploit what we already do well? Do you have any general thoughts on that?
Well, so the amount of stuff we could apply, the current techniques that we already have is mind-boggling, right? I mean, there's just not enough people who are trained to do this right now to kind of really do a good job at it. But so I think over the next 10 years or so, we're going to see a dissemination of deep learning AI technology in all corners of the economy, and at least that's what the economists are telling us. And perhaps have a measurable effect on productivity and economic growth and things like that. But I'm more interested in what's happening upstream, right? So there's a lot of really interesting concepts that people have come up with over the last few years that I found sort of have a lot of potential to kind of change the way we do things. So things like graph neural nets, for example, and graph convolutional nets, and invariant, equivariant neural nets, and there are libraries in PyTorch to do graph neural nets, some of which come out of my lab at NYU actually, and there are things like reversible models. So people are trying to sort of learn densities in high-dimensional spaces, and for that you need to have functions that you can invert for various reasons. Generative models, obviously, and then self-supervised learning we were just talking about. There's a bit of a debate, or not a debate, but like a lot of interesting things happening in self-supervised learning. It used to be that self-supervised learning was, it didn't used to be, but there are situations where in self-supervised learning, what the main paradigm is basically an autoencoder, right? You give an input, maybe it's corrupted a little bit, and you run it through a big neural net, and you train the neural net to recover the sort of clean version of it. That's called a denoising autoencoder, right? And that's what all the NLP systems use, the BERT style, Roberta, etc., right? And that's created a revolution in NLP. There's no question about it. This doesn't quite work just like that. You can't transpose this to the realm of images.
Yeah.
And the reason is because if you want to reconstruct an image, you have to deal with the fact that there are many, many different ways to reconstruct an image. In text, it's easy to handle the fact that there are multiple words that could be present at a place where you mask the word, and you can represent a distribution over all words, but we don't know how to represent distributions over images.
Yeah.
And so those things don't work. So the thing that actually works is what's called joint embedding methods, which draws on stuff that I worked on in the early 90s, and Jeff Hinton also worked on, called joint embedding architectures, a special case of which is Siamese networks. So
right, Dr. Lim and stuff.
Dr. Lim and various other algorithms of this type, where you have two neural nets that may or may not be identical, and you show it two different versions of the same image, and then you train the outputs to basically be the same.
Right.
And then you have some ways of making sure that when you show two images that are different, the outputs are different, and that's where things are hard.
Yeah.
For that, there are contrastive method and non-contrastive method. I'm really excited about a set of non-contrastive methods that people have come up with over the last year. So that is very exciting to me.
Nice.
Probably more exciting than a lot of stuff in the last 10 years, actually.
Yeah. I want to talk a little bit, sort of on the related subject, but actually very different. What do you think about the future of current machine learning frameworks? Where are they going to go?
I have very peculiar ideas about this. So first of all, I have to tell you about my own taste, right? My favorite programming language is Lisp. And for me, Python is an abomination. But of course, I know that Python is what people want because it's convenient, it's there's tons of libraries, there's already a lot of code, it's kind of easy to interface and everything. So Python is what people want.
Yeah.
Now, if you want to use Python as a front-end language for a numerical library, it's probably the worst possible choice, right? Because it's slow, it's not compatible, you can't type, the objects and things like that. And so it's horrible. But that's what people want, and you have to take that into account. So what's happening right now in the PyTorch framework and ecosystem and other places is that people are kind of trying to sort of inch their way towards kind of compiling more and more of the Python code, which I think is great, right? So there's all those efforts for there's the JIT, of course, in PyTorch. There's other attempts to do things like a functional version of PyTorch that looks a bit like JAX, where you can just write your function. That looks a little more like Lisp, actually. Things of that type that basically kind of fix the main limitations of Python. The other issue with Python is for productization, right? You want to have a self-contained piece of code without having to drag the entire Python runtime with you. And so, how do you detach your system, which most of the time is not just a neural net, but there's a bunch of code around it. So that again sort of raises the question of, is there going to be a future where either we sort of ease the community into something that looks like Python but basically is compatible and more compact and everything, or kind of a sort of two-language type ecosystem where the low level would be in kind of a domain-specific language that you can intersperse with Python code. So you were working with me at NYU, and you remember Lush, and Lush had this possibility: you would write Lisp code, and then you would do hash brace, and then you could write C code and refer to Lisp variables, and that was wonderful, right? Because you could intermix code any way you want. So that's kind of one of the directions that I see people going into.
Yeah.
And this may be sufficient.
Yeah.
We'll see.
What advice would you give to them on whether, let's say, they want to be a scientist or an engineer, separately, or maybe a hybrid of both? What would be your top things that they should go do?
Well, so it depends a lot on the type of career you want to have. But what I would my advice, which I've been giving for years in various contexts, is learn things that are difficult to learn when you're young and impossible to learn when you're less young. Okay, so these are things like physics and math, basically, right? You have to learn that stuff when you're young. And why am I saying you should learn physics? Like, why should you take a course? Like, if you had a choice between taking a course on, I don't know, mobile device development, software development, or quantum mechanics, take quantum mechanics. Why am I saying this? Why is quantum mechanics relevant to machine learning? Turns out it's the same math. Or statistical physics. It's the same math that you use for understanding deep learning systems, the dynamics of learning in high-dimensional spaces, those models I was mentioning earlier, invertible models, those are based on quantum physics, basically, unitary matrices and things like that. And there's going to be more and more uses of machine learning in the sciences, if you are interested in the sciences and research. So if you want to become a scientist, even a physicist, a chemist, a biologist, deep learning is going to be one of the main tools that is going to be able to take us forward. And if you have a sort of double expertise of knowing about machine learning and deep learning, but at the same time being a physicist, a chemist, or a biologist, or an economist for that matter, or just about anything, you're going to have a combination of skills that doesn't exist anywhere, and that makes you valuable. That makes you unique.
Yeah.
Try to make yourself unique. Now, the other reason I say take courses on quantum mechanics and linear algebra and probability theory is that this is knowledge that has a long shelf life that will kind of learn you to teach you to reason about certain things that otherwise you wouldn't have no idea about. Whereas if you learn a piece of technology that appeared in the last 2 years, it may disappear in the next 2 years. The model may be completely different, right? So learn things that have a long shelf life. Then if you want to make yourself known or remarked, just participate in an open source project. That's the best way. We didn't used to have that, right?
Right.
But now you can you can contribute to an open source project, and your name is on the Git, and you can claim that and get some credit for it, and it will kind of help you get noticed.
It makes sense. That's how I got my first and second jobs. So definitely would recommend that advice. I just wanted to close out on first, I want to thank you for taking the time to speak
Pleasure.
with us today. And do you have any other closing thoughts you wanted to talk to the community about anything else? Could be pretty much, the floor is yours.
I think there's going to be another revolution of AI over the next few years, probably due to the combination of things like self-supervised learning and things like that. If that revolution occurs within the next 5 years, I think we're lucky. It might take longer, and the question is whether it's going to take more time or longer than the patience of the people funding the research, who may get impatient, right? So we need to have household robots. We need to have machines with common sense, because in a few years or decades, we're all gonna wear augmented reality glasses, and we're gonna talk to our virtual assistant, who is gonna mediate our interaction with the digital world, is going to help us deal with the flow of information that we are bombarded with on a continuous basis. And for that, we need machines that can dialogue with us, that understand us, that have some level of common sense, understand how the world works, everything, all of that. And then, so those are the two big applications. Robotics, household robots, a robot that is as agile in terms of its mind, maybe not the mechanics, as a house cat. We don't have that. We're nowhere close to that.
Yeah.
And on the other side, on more of the reasoning and sort of human type intelligence, have sort of quasi-human level intelligence virtual assistants that we can talk to. Because we're not going to get our phone out of our pocket anymore, right?
Right.
We're going to have a virtual assistant that we can talk to through our augmented reality glasses. And so that's going to be a very different world. And we're going to live part of our life in the metaverse, right? So metaverse is going to be populated by AI agents, in addition to human, to sort of, to people. So a lot of possibilities there.
Very cool.
So Soumith, I know, I want to ask you a question. I know at Facebook you're working on robotics and things like this, there's a little bit of tinkering there, but do you have any sort of personal projects or personal interests that you might want to tell us about?
Personal projects. Well, I think this is very hard because to me, I have this philosophy that I only work on whatever is fun. If I don't feel like it's fun, then I don't work on it. So to me, work and personal aren't that far away from each other. The robotics thing you bring up actually started as a personal project. I was like, I need to build a robot I hate doing dishes and like loading up the laundry. Like, why in 2021 are humans still doing this stuff? Why can't something else do it for us? That's kind of how it started. And then I got into it enough that I kind of spend a lot of time on it these days, doing home robotics and stuff.
Right.
Yeah. What about you? Let me ask you. You have, I think, just knowing you for enough years, you have so many nerdy personal projects that are super cool. I'd love to hear some of that stuff.
I mean, there's stuff I like to do which are projects or not. So, I'm into sailing, I'm into astrophotography. And in fact, in astrophotography, you take a whole bunch of pictures during a whole night, and then you have to process the photos to kind of align them and get sort of higher resolution from what you get normally. And I actually wrote a PyTorch script to do this. Okay, you can just you can buy packaged software to do that, but I found that boring, so I actually wrote my own PyTorch script for that. I mean, it's using PyTorch and NumPy and various other things, but then the main kind of hobby, if you want, that I have is that I build electronic music instruments. In particular, I build electronic wind instruments. So I have those little things, which actually I talked about this in a talk that you can find on YouTube now, which are like, kind of like saxophone recorder like things that have a microcontroller and they talk to a synthesizer. And I put all kinds of sensors in them and all that stuff. And I've always been fascinated by the use of technology, computer technology in particular for music. The first computer I bought, which was in 1977, which was a single board computer, the first thing I did with it was, play music with it. So.
Very cool. Well, if you are actually tuned in to next year's PyTorch Dev Day, then we can get Yann to play some of his music instruments. Well, finally, Yann, I really wanted to thank you for being here today, and I really appreciate you taking the time. I know how busy your schedule is. And do you have any other thoughts you want to share or talk to the audience about?
Well, I want to thank you for being here also and having this wonderful discussion. I think the future of AI is likely to be very exciting. I think we're going to go through another revolution in AI, perhaps brought about by things like self-supervised learning. I'm really looking forward to it. I hope it happens before my brain turns into mush.
Let's hope for that together. So I hope you had a great time with this session, but I also wanted to ask you to go check out the really exciting talks we've had earlier today, especially on PyTorch Live, the new PyTorch release, the PyTorch ecosystem updates, and the talk that Lynn gave on our vision. So please go check that out. I'm really excited about this.